Hi and welcome to another video tutorial. In this video tutorial what I'm going to be doing is showing you a proof technique known as proof by mathematical induction. So I'm going to show you how to use proof by mathematical induction to prove things, but first of all what I'm going to do is go through the method. Okay, so the general method then. What do we have to do first in proof by mathematical induction? So the first thing we have to do is we have to prove what's called a base case. So we have something that we want to prove and we've got to show that it's true for a base case. Now what does that mean? That means we've got to show that the left hand side is equal to the right hand side for n is equal to 1. So when you substitute n into the left hand side and you substitute n into the right hand side, you get the same thing. So we've got to prove the base case. In other words, is this thing true for n is equal to 1? Then what we've got to do is we've got to assume that it's true for n equals k. So we can write down the left hand side and write down the right hand side with k substituted in, and this will help us to do the next step. So we're going to assume that whatever we're trying to prove is true for some value k. Then what we've got to do is show that it is true for n equals k plus 1. And there's two sub-steps to this step which I like to explicitly do, which is we've got to write down what our target is. So in other words, what we're trying to show but by doing our algebra. And then we show that the left-hand side of when we substitute k n is equal to k plus 1 into our thing that we're trying to prove is equal to the right hand side target. And then finally we write a conclusion. So we write maybe one or two sentences just to say just to explain what we've done and the fact that we've proved that whatever we're trying to prove is true. Okay, so this is a bit vague and a bit general. What I'm going to do now is show you how you apply this to some examples. So this is my first example. What we've got to do is prove that 1 plus 2 plus 3 plus so on until n, until some value n, is equal to n multiplied by n plus 1 divided by 2 for all of the integers n is greater than or equal to 1. Okay, so let's begin. So the first step then is we've got to prove the base case. So we've got to say to ourselves, is this true for n is equal to 1? So let's write down step 1 here. So we're saying to ourselves, is this true for n is equal to 1? So on our left hand side, we've just got 1, because we're saying if n is, so we're substituting in n is equal to 1, and on our left hand side we've just got n. So we're saying n is just equal to 1, and that's fairly straightforward. We're just substituting n is equal to 1 into the left hand side. So saying left hand side equals 1. Then the right hand side, when we substitute in n is equal to 1, we get 1 multiplied by 1 plus 1 divided by 2, which equals 1 times 2 divided by 2, which equals 2 over 2, which equals 1. So we can see there that the left hand side is equal to the right hand side, and then we'd simply say something like so the result holds for n equals 1. We've said 1 plus 2 plus 3 plus until plus n is equal to n multiplied by n plus 1 over 2 for the value n is equal to 1. So that's step 1. We've proved it for the base case. Now for step 2, we've got to assume that this is true for n equals k. So we're assuming that this here is true for n equals k. Now, what does that mean? Well, what we're saying is that 1 plus 2 plus 3 plus ... plus k equals k multiplied by k plus 1 divided by 2. So we're just going to say, right, we're going to say that that's true. We're not proven that that's the case. We're just saying, right, okay, that's true. And that's step 2. That's all we have to do for step 2. So we're substituting k into here and saying, okay, that's true. So now for step 3, we've got to show that this up here, what we've got here, is true for n equals k plus 1. So I've written under the, in our method, write down a target. And what I mean by that is we want to show that 1 plus 2 plus 3 plus ... plus k plus 1 is the same as k plus 1 multiplied by k plus 1 plus 1 over 2. And this here is what I mean by our target. So if we just simplify that a bit, so k plus 1, k plus 2 divided by 2. This is our target. So what we're going to be doing in this step is showing that this is equal to this. So I'm going to write that down so that when we do some algebra with this and we get to this, we know that we're finished. So just give ourselves a bit more room there. Okay, so first of all, we've got to write down our left-hand side again. And what we're going to do in this step, as I said just a moment ago, is do some algebra on this and show that it is this. It's the same as this. So what can we say that this is the same as? Well, we could say that this is the same as saying 1 plus 2 plus 3 plus ... plus k, in brackets, plus k plus 1. And that's the same thing, because we're just writing down this 1 plus 2 plus 3 plus ... and then the term before k plus 1 is going to be k, so we've written this bit of our sequence of numbers here, going from 1 plus 2 plus 3 plus until k, and then we've just put an add sign and then k plus 1. So this is the first step part of doing the inductive step, which is called step 3. So you've got to say to yourself, what is the term that comes before this term here, k plus 1? Well, it's k. So we're writing down this and then plus k plus 1. If we look back at our assumption now that we've made up here, we can see that the left-hand side of our assumption is the same as this. So what we can do is substitute in the right-hand side of our assumption for this part. Okay, so now we've got something we can work with. Now all we have to do is simplify this that we've got here until we get this. So what I'm going to do is multiply the top and the bottom of this, show that as a fraction, multiply the top and the bottom of this by 2 so we can add these two together. Then I'm going to add them together. Then I'm going to simplify this top here. And then I'm going to factorise the top of this. What I should get when I factorise the top of this is this top here. And you can check by multiplying those two brackets out that you get that. So this is the inductive step. What I've done is I've shown that this left-hand side here is the same as the right-hand side of our original thing that we had to prove when we substitute in k plus 1. So now I've nearly finished my proof by induction. All I have to do is write down a short conclusion. So I would write down something like, if the result holds for n equals k, because remember that's our assumption. Our assumption is that the result holds for n equals k, then the result holds for n equals k plus 1. So what we've shown by doing this inductive step is that if the result holds for n equals k, so if our assumption is true, then the result holds for n equals k plus 1. In other words, then what we're trying to prove is also true for n equals k plus 1. And then we just say by induction on n, 1 plus 2 plus 3 plus ... plus n is equal to n multiplied by n plus 1 over 2, or all n is greater than or equal to 1. Okay, so that's how you do proof by induction. That's a simple example, and hopefully that's made the general method that I've written up here a bit clearer. Now what I'm going to do is go through a further example which is slightly more complex. Okay, so here's my next example. What we've got to do is prove by induction on n that 1 squared plus 2 squared plus 3 squared plus ... plus n squared equals n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6 for all n is greater than or equal to 1. So that's for all positive integers greater than or equal to 1. So what have we got to do first? Well, if you remember when I went through the general method, what we've got to do first is prove that this here is true for n equals 1. What I'm going to say is when n equals 1, the left hand side is equal to 1 squared, which is equal to 1. Okay, and then the right hand side is equal to 1 multiplied by 1 plus 1 multiplied by 2 plus 1 divided by 6, which is equal to 1 multiplied by 2 multiplied by 3 divided by 6, which equals 6 divided by 6, which equals 1. And then all we need to say is the left hand side equals the right hand side, and therefore the result holds for n equals 1. Okay, so we've proved that it's true for n equals 1. That's our base case. The next step is to assume that it is true for n equals k. Okay, so I've written down what we had originally, apart from I've substituted n for k. So we're just going to say, okay, that's true. We're just going to assume that that's true. And that's going to help us with the next step of proving that this is true for all integers greater than or equal to 1. Next of all, we have to show that it's true for n equals k plus 1. What we do first of all is substitute in k plus 1 into the left hand side. And now I'm just going to write down our target. So we're trying to show that the left hand side is equal to what? Well, we're going to substitute in k plus 1 for n into the right hand side of what we had originally. So if we substitute that in and simplify it, the target comes out to be this. So how have I got that? Well, all I've done is I've substituted in k plus 1 for n into the right hand side of what we had to prove originally. Okay, so what can we say that this is equal to? This part plus whatever the previous term to k plus 1 squared is, plus k plus 1 squared. Okay, so then we get that. And then we look back at our assumption and we can see that this part of what we've got at the moment is the same as what we've got on the left hand side of our assumption. So we can substitute in the right hand side of our assumption here, and then we've got something we can work with. Okay, so now we've got this. Now a bit of algebra, and then we should be presented with our target. I'm going to write this as a fraction. By multiplying the top and the bottom of that by 6, I can write this as one fraction. What I can then do here is look and see that k plus 1 is a common factor to both of the terms on the top of our fraction here. So I'm going to bring k plus 1 out to the front and put some square brackets around the rest. Then I'm going to carry on up here. So I can simplify what's inside these square brackets to a quadratic equation. So I've simplified what's in those square brackets there to a quadratic equation. And then if I factorise that quadratic equation, what I end up with is k plus 1 multiplied by k plus 2 multiplied by 2k plus 3 divided by 6. And then you can see that that's the same as our target. We've proved that this up here is true by using mathematical induction. So I'll just give myself some extra space, and then I can do the final step, which is to write our concluding statement. So I can say if the result, and by the result what I mean is this up here, what we started with and what we had to prove. If the result holds for n equals k, then it holds for n equals k plus 1. So by induction on n, 1 squared plus 2 squared plus 3 squared plus ... plus n squared is equal to n multiplied by n plus 1 multiplied by 2n plus 1 divided by 6. And there we have it. We've proved this result by mathematical induction.